The signal changes, but the crossing does not immediately begin. At a wide urban intersection during the late afternoon rush, a steady line of pedestrians gathers along the curb. Vehicles continue to pass through the junction, clearing the last phase of traffic before the right-of-way shifts. Above the waiting crowd, the pedestrian signal transitions. From a static symbol to a display that includes a number, the number begins to decrease second by second before the first step is taken. This numerical display the countdown. Timer does not alter the rules of the crossing. The signal still determines when movement is permitted. Yet the presence of the timer changes. How the transition between phases is managed, not only for individuals, but for the system that governs the intersection as a whole. The countdown timer appears most clearly in environments where traffic flow is dense and timing precision is necessary. Intersections in urban centers operate on fixed or adaptive signal cycles. These cycles allocate time across competing movements, vehicles proceeding straight, turning traffic, and pedestrians crossing in one or more directions. The duration of each phase is calculated based on roadway width, expected walking speed, traffic volume, and safety margins. Before the introduction of countdown timers, pedestrian signals typically displayed only symbolic states walk or do not walk. In some systems, an intermediate flashing phase indicated that the crossing period was ending. This structure communicated permission and restriction, but it did not convey duration. The remaining time within a phase was not directly visible. From an institutional perspective, this absence of visible duration created variability in how crossings were interpreted, pedestrians arriving at different moments within the same signal. Phase made decisions under uncertainty. Some would begin crossing late into the allowed period, while others would wait even when sufficient time remained. These differences introduced inconsistency into the system, affecting not only pedestrian movement, but also the predictability of traffic signal cycles. The introduction of countdown timers addressed this variability, not by changing the underlying rules, but by standardizing the way time is represented within the crossing phase. Instead of a binary or symbolic indication, the signal now provides a continuous numerical reference. This allows all participants, regardless of when they arrive at the curb, to align their decisions with a shared understanding of remaining time. The adoption of countdown timers did not occur simultaneously across all regions. It emerged through a combination of local trials, safety studies, and updates to traffic engineering guidelines. Municipal transportation departments evaluated intersections with high pedestrian volumes or frequent conflicts. In these locations, observational data showed that late crossings and hesitation at the curb contributed to inefficiencies and potential safety risks. By introducing a visible countdown, institutions aim to reduce these inconsistencies. The timer provides a reference that is independent of individual judgment. Instead of estimating whether there is enough time to cross, pedestrians can observe the remaining seconds directly. This reduces the likelihood of initiating a crossing when insufficient time remains, and it encourages more uniform behavior across the group. Standardization played a central role in this process. Traffic control systems rely on consistency across intersections to maintain predictability. When countdown timers were incorporated into official guidelines, their design and operation were specified in detail. The numerical display, its placement within the signal, and its synchronization with the signal phases were all defined to ensure that the information presented would be interpreted consistently. These standards also extended to the calculation of crossing time. The duration displayed by the countdown timer is not arbitrary. It is derived from assumptions about pedestrian walking speed and crossing distance. These assumptions are codified within engineering manuals and adjusted over time as demographic and environmental factors change. For example, revisions to walking speed assumptions reflect broader considerations of accessibility, ensuring that the timing accommodates a wider range of users. The integration of countdown timers required coordination between hardware, software, and procedural frameworks. Signal controllers had to be capable of managing the numerical display in synchronization with the signal phases. Maintenance protocols were updated to include the additional components. Training materials for traffic engineers and technicians incorporated the new standards, ensuring that the system could be implemented and sustained across different jurisdictions. Over time, the presence of countdown timers became a stable feature of pedestrian infrastructure. Their function is now embedded within the expectations of both pedestrians and drivers. Drivers anticipate that pedestrians will respond to the visible countdown, adjusting their own behavior accordingly as the signal phases change. Pedestrians, in turn, rely on the timer as part of the crossing environment, using it to coordinate their movement with the broader flow of traffic. The stability of this system depends on repeated use under consistent conditions. Each cycle of the signal reinforces the relationship between the numerical display and the underlying timing of the intersection. Through repetition, the countdown timer becomes less of an explicit instruction and more of an integrated component of the environment. It operates within the background of the crossing process, shaping behavior without requiring conscious interpretation. This integration also reflects a broader institutional approach to managing shared spaces. Urban intersections are points of convergence, where different forms of movement intersect under regulated conditions. The effectiveness of these systems relies on the ability to coordinate actions across large numbers of participants with minimal direct communication. Standardized signals, including countdown timers, provide a common reference that supports this coordination. The continued use of countdown timers is tied to their compatibility with existing traffic control frameworks. They do not require a fundamental change in how intersections are managed. Instead, they extend the informational capacity of the signal within the established system. This allows them to be incorporated into a wide range of environments, from dense city centers to suburban crossings, without disrupting the underlying structure of traffic control. As signal technology evolves, including the use of adaptive systems and sensor-based controls, the role of the countdown timer remains consistent. Even as the timing of signals becomes more responsive to real-time conditions, the need to communicate the remaining duration of a phase persists. The countdown timer continues to serve as a bridge between the internal logic of the signal system and the observable environment experienced by its users. At the intersection, the number decreases to 0 and the signal changes again. The transition is not abrupt. It follows a sequence that has been repeated thousands of times. The presence of the countdown timer ensures that this transition is not only governed by the system, but also understood in a consistent way by those who move through it. The object remains in place because it aligns with the requirements of the system it supports. It translates a temporal process into a visible form that can be interpreted uniformly. Through standardization, adoption, and repeated use, the countdown timer has become a stable element of pedestrian infrastructure, continuing to function as part of the coordinated movement of everyday urban life.